So last time we basically talk about random variables. And for a random variable, we usually use capital letters to denote them. Okay. So this is essentially a mapping that maps each outcome in the omega space to a real number. Okay. So it assigns a real valued statistics to every outcome of the experiment of interest. And for this random variable, we have defined, we have introduced two important distribution functions. One is the cumulative distribution function, which we call CDF. And the notation for that is capital F subscript capital X, and then evaluated at any real numbers, which is denoted by small x. Now, the precise meaning of this CDF is defined as the probability of this event. The probability is such that it's the probability of the event that this random variable, the value of this random variable is smaller or equal than x. And this probability is evaluated in the probability space associated with this random variable. Now, if we want to go back to the original space, so that is where the specific meaning of this cumulative distribution function is precisely defined. So if we go back to the original space, this event is actually denotes the set of all the outcomes such that it's the set of omega, set of all the outcomes omega. Okay, to be more precise, the set of outcomes omega such that their corresponding random variable. Remember, the random variable assigns real values to every outcome. So for every omega, the random variable will assign a corresponding real value. So x omega is a value. Is to collect all the outcomes omega such that x omega is less than x. And clearly, this set is collects a bunch of elements from the omega space. So it is a subset of omega. Therefore, it is an event. We call this an event in the original probability space. Now, for this event, we can for sure evaluate its probability by using the probability law associated with the original probability space. Okay, so this is the precise meaning of this cumulative distribution function of a random variable. So essentially, when we calculate this function, we need to calculate the probability of a certain event. And this event is defined by, it really depends on how we define this random variable. And then we talk about another function called PDF, probability density function. Now this function is defined whenever the CDF is differentiable. So we define the PDF simply as the derivative of CDF. Whenever it's differentiable. Now, sometimes the CDF may not be differentiable at certain points. We have seen the examples last time. So at those discontinuous points, we use delta functions to denote their derivative. So that is a way to define the PDF function for non-continuous CDF functions. So this is the PDF function defined based on the CDF. So as we can see that the fundamental function associated with a random variable is the CDF function. This one is the most fundamental one. In any case, we can always have a CDF. But for PDF, it depends on the differentiability of the CDF function. And then based on these definitions, last time we introduced a concept called conditional CDF. This is very similar to the conditional probability. Basically, the idea is we look at this CDF function and then we conditioning on a certain event E. Well, this E is an event of the original omega space. Now, this notation, this definition, precisely, it means that if we write down the definition of the CDF, now the CDF part corresponds to the probability of such an event. Okay. And now this is conditioned on E, on this event. Now, precisely, we can write out this. We can expand this conditional probability expression using the definition of conditional probability. So we know this E is an event in omega, and we also know that this x less than or equal to small x. This is also an event in the omega space, as we have denoted here, right? This is also event in the omega space. So both of these events are in the omega space. So we can just follow the original definition of conditional probability. And by that definition is probability of the joint event. Well, joint event is the intersection of both events and divided by probability of E. And this really makes sense because both of these events are events of the original probability space. So we can, by the sigma algebra, we can take their intersection. Okay, and the intersection event, this joint event, is also belongs to the sigma algebra. And then we can evaluate the probability using the probability law associated with the original probability space. Okay. So this is the precise definition of this conditional CDF. It's basically the probability of the joint event over the probability of this conditional event. Okay. And then similarly, we can also define this conditional PDF function. Which we denote as the original PDF function conditioned on the event E. This is the notation. Now, the precise meaning of this, again, originally when we define PDF function, we define it based on the derivative of the CDF. Right? So following the same logic, we can define the conditional PDF following the derivative of the conditional CDF. Of course, this requires that this conditional CDF is differentiable. Okay. So basically, so first of all, this conditional CDF is always well defined because it has this precise definition. And whenever this conditional CDF function is differentiable, we take the derivative, and that is called the conditional PDF function. Okay, we can consider one example. So consider this event defined as it's defined as a random variable x takes values between x1 and x2. Okay. Of course, here we omit the underlying probability space. So more precisely, we can, so this denotes the event in the original omega space. Okay. Now let's consider the conditional PDF under such a event. So looking at this conditional PDF. And in the previous lectures, we have one example since lecture 8 right here. Yeah. Okay, in this, when we talk about CDF functions, when we talk about conditional CDF functions, we have this example, the same example where we are looking at the same event and we calculated the expression of the conditional CDF conditioned on this event. So it turns out that the CDF function, this is a function of x, takes the following formula. It depends on the value of x. Okay? If x is smaller than x1, CDF is 0. X bigger than x2, CDF is a constant 1. And in between, the CDF takes this form. Okay? And you can see that x1, x2, these are constants. So these are numbers. These are numbers, certain constants. But this is the function. This is a CDF of x. So this is the function itself. And then so we already have the form of the conditional CDF. So by definition of this conditional PDF, we just need to consider the derivative. Okay. So basically, we just need to take the derivative of this function, this entire function. And you can see that in these two parts, in these two regions, they are constants. So the derivative is 0. So the only thing we need to care about is in this middle region. And taking the derivative, well, following the derivative law, this is just this constant multiplied by the derivative of the CDF. Okay. So following that, we know that the derivative is 0 when x is less than x1 or greater than x2. Okay. Now in between, we take the derivative of this one. Now taking the derivative, capital Fx becomes the PDF. Okay. Okay. So this becomes the PDF after taking derivative. And this is a constant, so we can ignore it. And divided by a constant, so by the derivative rule, so we will need to scale this derivative by the same constant. So it takes such a form. So it's basically the PDF of the unconditioned PDF scaled by a constant. Yes.
So the bound for this x1 less than 4x. But the one that the example you're showing us is x1 less than this. So
Yeah. I think this should be consistent. Yeah, this should be less than x1. Yeah, and then this is less than equal to greater than equal to x1. Okay. Right. Now consider another example. Let this sequence of events be a partition of the omega space. And each event has a positive, strictly positive probability. Okay. Remember the partition. That is a set of disjoint, a set of mutually exclusive events that covers the entire omega. So that is a partition. And then let's consider this another event which is defined by a random variable. So this is another event in the omega space. Okay. Now we can, because we have partition here, so we can apply the total probability law. The total probability law says that we can decompose the probability of an arbitrary event. Now, in this case, we consider this event. We can decompose this the probability of this event using this partition. Right. So this is a partition, total probability law. Is the probability of each partition event multiplied by the probability of the event of interest conditioned on this partition event. So it's like a weighted summation of this conditional probability and then summing over all the partitions. Now, why do we want to look at this form? Because on the left-hand side, this is exactly the definition of the CDF. This is a CDF. And on the right-hand side here, this is the definition of conditional CDF. So you can see that for a random variable, its CDF function can also be partitioned in this way. It's a weighted sum of the conditional CDF functions. This is over a sequence of partition events. Now we can further take, if we assume they are differentiable, we can take derivative on both sides and also conclude that for the PDF function, it also has this partition rule. So taking the derivative on the right-hand side, now the only thing related to x is this conditional CDF function. So we take derivative of this conditional CDF, and that becomes, by definition, the conditional PDF function. Okay. So gives us another way to calculate CDF and PDF. If we have a natural partition of the underlying random experiment. And sometimes we are interested in such a conditional probability. It's a probability of a certain event conditioned on a certain random variable takes a certain value. So this is an exact form. This is different from this inequality form that we talked about before. So this event, this conditional event is when this random variable takes this exact value x. And we can transfer this probability, conditional probability, into a form that is related to the PDF of random variable x. Because in general, this event is relatively hard to characterize. It is not in an inequality form, but we can always write equality as a limit of inequalities. So that is the first idea. Okay, I let epsilon goes to 0, decrease to 0. And then this, when epsilon goes to 0, this essentially, now think about that. When epsilon becomes a very small positive number, on the left-hand side, capital X needs to strictly bigger than, okay. Let's try to visualize this. So this is X. X minus epsilon, strictly bigger than X minus epsilon. So this is X minus epsilon. And less than or equal to X plus epsilon. Okay. Now you push this epsilon to 0 so that these two ending points, they are converging to X from both sides. Now in the end, the only element left is X. Is X, because this is less than or equal to. So this part contains X. And the left part will exclude everything that is smaller than X. So in the end, the only element is X. So this equality, this event can be viewed as this event going to the limit. And now this form, for any epsilon, this form can be related to the CDF and PDF functions. So let's look at that. Okay, now this is a conditional probability. So I just follow in the definition of conditional probability. Actually, following the Bayes rule, I can write it in this way. It's PA right? This is basically the probability of the joint event, okay, between A and this event, right? It's PA times P, this event conditioned on A. So this is essentially the definition of the joint probability. And then the denominator is this conditioned event. And I can introduce these additional factors. It's basically one. This is one for any epsilon. But the thing is that then I can combine this part and this part. If you look at this, so these two parts, they are the same. If you look at each one, is the probability of this conditional event divided by 2 epsilon. Well, 2 epsilon is the kind of the length of this interval. So by definition, this is when we let epsilon goes to 0, this becomes the conditional CDF, a conditional PDF. Because this is a form of the derivative. This is basically the derivative of this PDF as conditional CDF, taking derivative over X. And that by definition, this becomes the conditional CDF. Sorry, conditional PDF. And the denominator, again, is this can be viewed as the derivative of the original CDF function, right? Here we don't have any conditioning. It's just original CDF function, the derivative of the original CDF function. So by definition, taking a derivative, it becomes this PDF. When we push this epsilon to 0, these parts becomes the derivatives. So this is the final form that corresponds to this conditional probability. So this means that if we want to calculate this conditional probability, we can compute it by leveraging the conditional PDF and the PDF function of this random variable. Right, so sometimes this is very useful when we deal with this kind of events. And the Bayes rule for the probability law can be generalized to the PDFs. So if we consider any event A, and then we have the random variable X, then we have the following equation. we have seen a similar form of this when these PDFs are the probability of this event. So that in that case, both sides is simply the probability of the joint event. But this equation says that we can further take the derivative, and so the probabilities will become the CDFs will become PDFs. Well, we can actually verify this for the left-hand side. Yeah, this is conditional PDF. Right? So it follows from the equation that we just derived. From the equation that we just derived, if you multiply both sides by this PDF, okay, on the left hand side you have this one multiplied by the PDF, which is the left hand side, and what is left here is the PA multiplied by this conditional PDF. So again, this is a very special equation regarding this kind of events. Okay, it's the event when x takes a specific value, small x. And we also have this total probability law, which is different from, well, when we talk about total probability, right? We always need a sequence of events that partitioned the entire omega space. But here, the random variables, they naturally forms a kind of partition. So we have this equation. This PA can be decomposed in the following ways. Okay. So the intuition for this is that you can view this as a partition of the entire omega space. And this is the kind of the probability, it's a density function, right? So it's kind of the probability of this event, of this partition event. And because in many cases this x is a continuous form, so we take integration instead of summation. Okay? So it's kind of it has a very similar form to the total probability law that we introduced in the discrete case. So we can partition any the probability of any event based on the PDF of a certain random variable. Okay. So in many applications, we will see many examples that this random for a specific random experiment, we always have a corresponding random variable that naturally partitions that forms a partition of the omega space. So I think that is everything that we need for the midterm one. And for the rest of the time, we can work on the homework problems. So I plan to start from homework 5. Okay. And if we have time, next time we will comment on homework 4. So homework 5 is all about conditional CDF, PDF, conditional CDF, and conditional PDF, and all these rules that we just talked about, total probability, Bayes rule, this and that. Okay, so let's look at the first problem. And here I will not go over all the calculation steps. Okay, I will just highlight the main idea and key steps. You will still need to complete homework 5 and submit before the deadline. I think the deadline is October 9th. Okay, let's look at the first problem. Consider a random variable C that takes values between 0 and 1, and suppose the PDF is given by this form. Okay. We need to find the constant K. Okay. So we have this given PDF function, but there's an unspecified parameter K. So the question is, find K. So this means that there must be some underlying properties that constrains the choices of K. There must be some properties about the PDF function, right? That constrains the choice of the K. So what kind of properties of the PDF can you think of for computing the subject K? So remember, this is the PDF function associated with a random variable. So when we introduce the PDF functions, and that is right after CDF here, there are some properties. Okay. It must be non-negative for all x. So here, this PDF takes K times C, and 0 otherwise. The 0 is no problem. 0 is always non-negative. K times C for C between 0 and 1. So in order for this to be non-negative, this K has to be non-negative. Right. So K has to be non-negative. And the second property says that basically the integration of this PDF over the entire support of X should be 1, right? So when you sum up all the probability densities of a random variable, it has to be accumulated to 1. So this is the key property. So we need to make sure that integration of, well, if you integrate this PDF over the entire real line, because this is 0, so we don't need to care about this case. So all we need to do is to integrate over this interval. Right? the integration, this is the density function dc, and over c from 0 to 1. Okay. This has to be summed up to 1. And this is an equation on k, right? Because the integration is over c. Now you work out this integration, it's k times c square over 2. Okay. And then you can do the rest of the calculations. Right. So the part A is very it's very simple if you notice this fundamental property of PDF function. Okay, now part B. For every value C, there is a corresponding coin. And here's how it works. If coin C is selected and flipped, so basically, if this random variable C, capital C, it takes a value small c, then we will select the corresponding coin C and flip it. Okay. Now, if this coin C is selected and flipped, the probability of getting heads is given by this one. Probability of head, even that we flip the C's coin, is small c. Okay, so for different coins, they have different probability of heads. Now, this is our experiment. We first randomly select a coin corresponding to the random variable C. Okay, we draw a realization of random variable C from the distribution, from this PDF. And then once we have this small c, we select the corresponding coin and flip the coin. And we need to find the probability of head for this experiment. Right. So there are two. This is like a two-step experiment. First step, you draw a realization of this random variable, and that determines which coin you will flip. In the second step, you choose that coin and flip it, and then you will see a head or tail depending on this distribution. And we have seen similar examples before. So in this case, the second step depends on the consequence of the first step, right? So therefore, the first step, the outcome of the first step naturally forms a partition of this experiment. We have comment. Is it a PDF in part A? Can you be more specific? Are you talking about part B or part A?
When you were explaining part B, you referred back to the PDF in part A. At least that's what I understood. And I wasn't clear to me that part B was a continuation of part A.
I see. Yes, it is a continuation of part A. Yes. So basically, when you draw a realization of this random variable C, you follow part A, you follow this PDF to draw a realization. And once the realization C is observed, you go ahead and flip the C's coin.
Okay.
Yeah. So A and B. I think A is shared by all the subsequent parts. So we will see. Yeah, at least for part B, it is a continuation of part A.
Okay, thank you.
Okay, so here we are going to use it's basically the partition, total probability law. So the probability of heads okay, so we can first illustrate the entire process of this experiment. So we draw a realization of this random variable based on its PDF in part A. Once this C is selected, we flip the coin. So, and then the probability of head given that we flip this coin is C. So apparently to observe the head, we must know which coin that we flip in the first step. So we can leverage the total probability law. Right, this is the total probability law that we just discussed. We go back here. Probability of any event can be decomposed in this way for any random variable. If we know the PDF of this random variable, and if we know how to compute this conditional probability. In this case, this random variable C is the choice of the random variable that we need to consider here. Because on one hand, we know this PDF of this random variable from part A. Okay. On the other hand, from the statement of the problem, we know that flipping this coin depends on the choice of the coin depends on the realization of this random variable. So when we compute this probability of head, we should always condition on the selection of the coin. And this one is also given by the problem. We know the distribution of head for a specific choice, for a specific coin. And we also know the distribution of these coins. So both parts are given. And we just need to plug in this. This is given as C, right? And this is given from by part A. Once you specify the K in part A, and then the entire PDF is very clear. So you plug them into this partition rule, total probability rule, and you can do this integration, you can get the result. So this integration will be between 0 and 1. So this is the original form where we always integrate over the entire real line. But then this PDF is only supported between 0 and 1. So in the end, your integration should be between 0 and 1. So this is part B. Okay, so in this case, using the total probability law of random variables is very natural, because this event critically depends on the realization of this random variable. Okay. So that motivates us to consider this total probability law for random variables. Okay, now let's go to this next part. Okay. Consider this event. We need to calculate the probability of this event. Now, what is this event? We randomly choose a coin corresponding to the value of the random variable C Okay, so we draw a realization of this random variable and then select the corresponding coin. Now, once that coin is selected, we will flip the selected coin n times. Okay, so the same coin is flipped n times. And this event says that among these n times of coin flips, we will observe exactly k heads. Now we need to find out the probability of this event. So in the end, once we determine the selection of the coin, let's say we choose coin C. Once we draw a realization of this C, capital C, right, and we select this corresponding coin C, we are going to flip it n times. So this is a repeated trial, unrepeated trials, kind of Bernoulli. I think it's a Bernoulli repeated trials, because we are going to flip the same coin, okay, the same coin n times, and they are independent. Okay. Among these n times, we observe k heads. So we have discussed this kind of experiment when we talk about Bernoulli random variables or Bernoulli trials. So again, this is a two-step process where we first select the coin and then we are going to flip the coin n times. So therefore, computing this event conditioned on the realization is simple. Suppose we are given the choice of the coin. Suppose we are given the choice of coin. Then for that, computing the probability of k heads among n trials, it is just a Bernoulli repeated Bernoulli trial, right? So n choose k. This means that we have k heads and n minus k tails. Right. And then we have k heads. Now, what are the probability of observing a head? Well, given this C, given this coin, the probability of head is small c. So we observe this heads k times, and then the probability of observing a tail is 1 minus c, which we observe for n minus k times. Right. So this is this conditional probability. Once we fix the choice of the coin, we know how to compute this. But what we need is probability of E. Okay. Therefore, we need to further consider all different cases of this random variable, and that is basically a total probability law that we just mentioned. Right? Because in this case, again, this is a two-step experiment, right? This is the second step of the experiment. Once we know which coin we select, the second step is relatively easy, right? So, but the second step depends on the first step. So we use the total probability law to decompose this probability into two steps. Now, this is the first step where we draw a realization of the coin. And then in the second step, once we fix this coin, we know how to compute this conditional probability. Okay, so this is the formula. Now, this conditional probability is given by this one. You can plug it into this formula. And this PDF, again, is given by part A. Okay. So once you figure out part A, you plug it into here, you do this integration. Okay. So if you do not know how to compute this integration, you can just leave it in this form. Okay. I think the critical part is that you figure out these two. The integration is a little bit complicated.
Isn't there a hint for solving the integration in the homework?
Oh yes. Oh yes. Yeah. Right. This is the yes. We need this one. Yeah. In the end, you will have well. See, you have this c to the power of k1 minus c to the power of another thing. This is exactly this hint. Yes. And you can leverage this hint to calculate that integration. But in the end, you can get a relatively simple result. Okay, that's the part C, and part D, we need to compute this conditional PDF. Conditional PDF. And by definition, yeah, so we refer to the definition of this conditional PDF. Now, this definition is given by in the derivative form. Okay, so we need to figure out. I think here, so basically, this event E is a yeah, okay, we can do it in this way. So following the Bayes rule, we need to leverage this one, I think. So we need to compute this. We need to compute this conditional PDF, right? And we are conditioning on any event A. So in this case, this A is this event E, okay? And we can follow this Bayes rule. So we basically divide both sides by PA, and we get this conditional PDF. And following this Bayes rule, we get but this is the Bayes rule, right? Exactly the Bayes rule. We divided both sides by PA. We have this. Now the nice thing is that when we applied Bayes' rule, this condition is this C and E, their positions are switched with each other. Right? So directly computing this one, computing C given E is very not very clear. But we know how to compute probability of E given C, given the realization of the random variable C. So that's why we need to use the Bayes rule to simplify this condition. And then this one is given in part A. PE is given in part C, given by part C. And this one, well, is also given by, by part C, right? So we have we have everything. Yeah. Yeah. So we need this one, right? So then from the Bayes rule, we just need to we can solve for this conditional PDF by using this equation. So following this Bayes rule, this conditional PDF is given by this product divided by PA. Yeah, and that is exactly what we have here. And if you use Bayes rule, then all the three components, all these three quantities, they are already given in the previous parts. So yeah, if you get the right results in part ABC, and I think if you plug them into this equation, simplify them. The simplification may take a little bit, may take some steps because it involves relatively complex expressions. But in the end, you will get a result. You will get a relatively complicated result. I will not write it down here. And the last one, okay, again, we first choose a coin by following the random variable C. And this time we flip the selected coin n+1 times. Okay, the same coin, flip it for n+1 times. Find the probability that heads appears in the n+1's toss, given that K heads has appeared in the first n tosses. Okay. So this is very similar to part C. Well, the only difference is that in the second step, we are doing different, we are looking at different probabilities. Here, we are looking at the probability that we observe K heads out of n trials, right? But here, we are looking at this event. Okay, the event that the head appears in the last toss, conditioned on the event that in the first n tosses we have K heads. Okay, so what we do is to following the same logic. We first fix the coin. We'll consider the randomness of the coin later. Let's assume that we fix a coin C. Okay, we fix the coin C And once this C is fixed, let's compute this probability. Okay. It's the probability that had in the n+1 toss, in the last toss. Okay. Given that K hats appeared in the first n tosses, now this conditional event is exactly this event E in part C, right? It's exactly this event. Flip, because in part C we consider flip the coin n times and observe K hats. So it is exactly the event E in part C. Okay.
Would you repeat that last part? It's exactly the event, what?
So here, right, we are, okay, look at this conditional event. Given that, now this is where the condition starts. Given that K hats appeared in the first n tosses.
Okay,
In part C, we're also looking at K hats in the first n tosses.
correct.
So this conditioning event in part E is exactly the event that we considered in part C. So that's why I use the notation capital E to denote this conditional event.
Okay. Okay.
Followed from part C. Because we will use, I think we will use some results there.
Yep. Got it. Thanks.
Okay. So this, okay, this is when once we fix the realization of this coin, we just need to compute this conditional probability. Okay, and then we just follow the conditional probability rule. So it's a joint event. We observe a head in the last toss, and also we observe K heads in the first n tosses. Yeah, given that we are flipping the coin C. Okay. Now this part, we can do it. So what is this part? The denominator is we can just calculate it by, this is a joint event. So we know from the previous parts, we know how to calculate this. So this one is basically this multiplied by the density of C, right? Well, let's check the nodes to be careful. I think it's here. Right, if you multiply both sides by this PDF, we have PA given this event multiplied by the PDF. So this is PE given this event multiplied by this PDF. So that's the denominator. But the real challenge here is the numerator. Numerator is the probability of this joint event. Okay, now what this joint event says is that we are flipping coin C for n+1 times. And in the first n tosses, we have K, we observe K heads, and in the last toss, we observe a head. But the first n toss is independent from the last toss, so we can compute them one by one, right? So the so this one, okay, so this is given by this one, and let's look at the numerator. This is given by okay, this is given by this. We adjust the conditioning on the realization of the coin and multiply by the corresponding probability density. Okay, now this part is where we can compute probability using combinatorics. Now we are conditioning that we are flipping the coin C. Now you tell me what is the probability that when you flip it n+1 times, you observe a head in the last toss, and at the same time you observe K heads in the first n toss. So this is given by no, the last toss. You observe a head in the last toss. That is probability C, because every trial is independent. So in every toss, this coin C shows up a head with probability C, right? So that's this one corresponds to the last trial. And this event E, we have done that before. So we have K heads among the first n trials. So the probability is this. It's this one. And then you multiply by the density. Okay.
Yeah.
This C corresponds to this one, right? The last toss, the n+1 toss, the last toss we observe a head. Yeah, that is independent from all the other trials. And given that we are flipping the coin C, this happens with probability C. Okay. And you can put everything together. I think in the end, well, actually, we can. Yeah, okay, there's some mistakes here. So we are we are looking at this one first. Now think about that. The probability that we need to compute is this one. Is this one from the problem statement. Find the probability that has appears in the n+1 toss given K has appears in the first n tosses is exactly this probability. And here we are not conditioning on the selection of coin. And by the total probability law, this is what we are gonna use. Because again, everything depends on the which coin that we select, and the selection of the coin follows from this random variable. So we need to use this total probability law to decompose it. So when we compute this integration, we need, now this one is given, so we just need to calculate this one. That's why we start with this one. That's why we start with this one. Okay. And I think and then once you have this one, you follow in these steps, right? You get this one, you can plug it back into this integration, do the integration and get the results. I think here we can just condition on C. We can just condition on C. So we leave this conditioning always. We leave the selection of C always in the conditional part. So this part is already computed in the previous parts. So for the numerator, we don't even need this one. This conditional probability can be computed. Now, in the end, you plug them back into this integration and calculate the results. Yeah, so the first problem is a little bit complicated, but essentially it is application of the total probability of random variables. Okay, so for the rest of the problems, we will do it next time. I will see you in the office hour in this afternoon.